11.4 Fundamentals of Probability. Any occurrence for which the outcome is uncertain is called an experiment. Thus, tossing a coin is an example of an experiment. The set of all possible outcomes of an experiment is the sample space of the experiment, denoted by a capital S. The sample space for the coin tossing experiment is the set that consists of heads and tails, everything that's possible when you flip a coin. An event, which is denoted by a capital E, is any subset of a sample space. So the events for tossing a coin would be the event that you could get a head or the event of getting a tail. If an event E has equally likely outcomes, and that's going to be important, equally likely outcomes, and its sample space has equally likely outcomes, the theoretical probability of that event is denoted like this, and it's simply the number of ways the event in question can happen divided by the number of ways anything in the sample space or any way an outcome of the sample space exists. For example, if you're talking about rolling a single die and you want to know, what's the probability that you roll a 5? Well, a single die has 6 sides on it, numbered 1, 2, 3, 4, 5, 6. So there's 1 5 out of 6 possible outcomes. The probability you're going to roll a 5 is 1/6. The probability that you're going to roll an even number, you need to see how many numbers are even. 2, 4, 6. Since there's 3 ways that can happen, again, out of 6 sides of a die, goes without saying, fractions always have to be reduced. So the probability of rolling an even number on a simple 6-sided die is 1/2. Events that are certain to occur are assigned probabilities of 1 or 100%. In other words, what's the probability that you roll a number less than 7? Well, how many numbers in your sample space are less than 7? 1, 2, 3, 4, 5, 6. Out of 6 values in the sample space, 1. A 100% chance you will roll a number less than 7 on a 6-sided die. By contrast, if an event cannot occur, its probability is 0. So what's the probability that you roll a 7? Well, how many elements in the sample space are a 7? None of them. Out of 6 possibilities, 0. Probabilities of events are expressed as numbers ranging from 0 to 1 or 0% to 100%. We normally are going to leave our probabilities as fractional or decimal values. You could convert those values to percent if you want, but typically we leave probabilities with fractions or decimals from 0 to 1. The closer the probability of a given event is to 1, the more likely it is that the event will occur. The closer the probability of a given event is to 0, the less likely it is that the event will occur. For example, if the weatherman predicts an 80% chance of rain, it's more likely to rain. If he predicts a 10% chance for rain, it's less likely to rain. The sum of the theoretical probabilities of all possible outcomes in the sample space is 1. In other words, if I wanted to find all the probabilities of rolling a single number on that die, the probability that you roll a 1 is 1 out of 6. The probability you roll a 2 is 1 out of 6. The probability you roll a 3, since there's 1 3 out of 6 possible outcomes, is 1 out of 6. The probability that you roll a 4 or a 5 or a 6 are all 1 out of 6. If I were to add those up, take their sum, Adding the numerators gives me 1, 2, 3, 4, 5, 6 out of 6, or 1. If our event is, we were talking about rolling even versus odd, the probability that you roll an even is 3 out of 6. The probability that you roll an odd, let's see, a 1, a 3, a 5, there are also 3 odd numbers on a die. So if I sum those, again, I get 6 out of 6, or 1. The sum of the theoretical probabilities of all possible outcomes in the sample space is always 1. That's going to be important to us later. Theoretical probability is based on a set of equally likely outcomes and the number of elements in the set. By contrast, empirical probability, sometimes known as experimental probability, applies to situations in which we observe how frequently an event occurs. For example, if you're doing a scientific research on the probability that this drug is going to cure whatever disease it is you're working on, you do a lot of experiments, right? And count the number of times of success, and the probability is the number of times your event happened over the total times you've observed the experiment. If we want to know what's the probability Michael Jordan will make his next free throw, and we've looked at the last 1,000 of his free throws, and we notice he made 995 out of the last 1,000, then that's the empirical probability that he will make his next free throw. Okay, let's see if we can answer some questions about some basic probabilities then. A die is rolled. Remember, we're always talking about fair die, fair coins. The set of equally likely outcomes is the set of numbers from 1 through 6. Find the probability of rolling a 4. Okay, so we write it like this. The probability of getting a 4. Since there's one number on a die that's a 4, there's one chance of getting a 4 out of 6 possibilities. The probability of rolling a number less than 3. So the probability of rolling a number less than 3, well, we got to find out how many numbers in the sample space are less than 3. That's 1 and 2, or less than 3. So 2 ways you can get a number less than 3 out of 6 total outcomes. Don't forget to always simplify those fractions. What's the probability of rolling a number greater than 4? Well, there's 2 ways, a 5 and a 6, that we can roll a number greater than 4 out of 6 possible outcomes. What's the probability of rolling a number less than 20? Well, how many numbers on a die are less than 20? 1, 2, 3, 4, 5, 6, all 6 of them, out of 6 possible outcomes, or 1. There is a 100% chance if you roll a 6-sided die, it will be a number less than 20. What about this? You're dealt 1 card from a standard 52-card deck. Okay, so let's refresh our memory of what a deck of cards consists of. There's 4 separate suits: hearts, clubs, spades, and diamonds. Each suit consists of 13 cards, the ace through 10, and a jack, queen, king. Okay, find the probability of being dealt a queen. So the probability that we're dealt a queen, I've got to count how many queens are in a deck. And there's a queen of clubs, queen of spades, queen of diamonds, queen of hearts. There's 4 queens, and there's a total of 52 cards in the deck. So 1 out of 13 is what that fraction reduces to. Oh yes, 13 cards in each suit, and 1 of every suit is a queen. What's the probability of being dealt a club? Well, There's 13 of each suit, so there's 13 clubs out of a total of 52 cards. And that reduces to 1 out of 4. Oh yeah, 4 different suits. One of those suits is a club. Probability of getting the queen of spades. Well, how many cards are queen of spades? Just one. Right, there's only one card that's the queen of spades out of 52 possibilities. What's the probability that you're going to get a diamond and a spade? Well, if you're dealt one card, right, one card, how many cards are diamonds and spades on the same card? None. You cannot draw a diamond and a spade on the same card. So that's another thing to continue to pay attention to as we go along, the difference between, are you talking about drawing one card or 2 cards or whatever? And we'll talk about those other options later, but right now one card cannot be a diamond and a spade. A fair coin is tossed 2 times in succession. The set of equally likely outcomes is listed right here. They can either both be heads. The first one heads, the second tails. The first one tails, the second heads, or both tails. That's every possible outcome. Find the probability of getting 2 heads. So the probability of getting a heads and a heads, when I look up here, that happens 1 time out of 4. So 1/4. Find the probability of getting the same outcome on each toss. In other words, both heads or both tails. Well, there's 2 ways that can happen out of a total sample space of 4. Find the probability of getting heads on the second toss. So I just have to count how many ways can that happen. Here's one and here's one. 2 ways out of 4. And don't forget, always goes without saying, you have to simplify those fractions. A pair of dice are rolled. Find the probability of getting, okay, a pair of dice, so 2 dice. Let me draw a chart over here just to give us an idea of what we're looking at, because remember, we've got to know what the sample space looks like, or at least how many elements are in the sample space. And it's a very common mistake. People say, well, there are 6 possibilities on each die, 2 dice. There are 12 total possibilities, but that's not accurate. Remember, our fundamental counting principle tells us that to count the number of ways something is going to happen, you multiply. So you don't add the 6 and the 6, you multiply 6 times 6 to get 36 possible outcomes. Let's look at what those look like. Okay, so both dice could have a 1 on it. Okay, and then the first one could have a 1 and the second one a 2, or one could have a 1 and the second one 3, or a 1 and a 4, a 1 and a 5, a 1 and a 6. That's every combination where the first die has a 1. Then we could do the same thing where the first die is a 2, and the second one could be a 1, a 2, a 3, all the way down to a 6. Now I'm not going to make the whole chart here, but we'll just look at the patterns until we get it figured out. Let's also look at these 2 rows right here. It might be easier to see that these are 2 different rows if we consider that maybe our dies were 2 different colors. Well, what if one die is blue and one die is red? Under that condition, let's look at these 2 rows. This is if the blue die is a 1 and the red die is a 2. And this is the row where the blue die is a 2 and the red die is a 1. Even though you get a 3 each time, these are two distinct, completely different roles. So I got to keep that in mind. And then we could just continue filling out this chart, imagining that if the first die is if the first die is a 3, then the second one could be a 1, or a 2, or a 3, etc., etc. And I could continue the chart by thinking about the first die being a 4, and then every combination of the second or the first die being a 5, or the first die being a 6, and then the second die being a 1 or a 2 or a 3, all the way down to the second die also being a 6. So notice 6 times 6, this is a square of 36 possible outcomes. So keep that in mind anytime you're rolling a pair of dice. So you want to find the probability of getting a sum of 5. Okay, and when you're rolling 2 dice, you always count the sum of the dots showing. So if I look over here on my chart, here's one way to get a 5, a 1 and a 4, and notice my numbers are in the diagonal. A 2 and a 3, a 3 and a 2, a 4 and a 1. Every way of getting a 5 is right here. Every way of getting a 6 is right here. 1, 5, 2, 4, 3, 3, 2, 4, 1, 5, 5, 1. Right? All of the 8s are on this diagonal. So for a 5, I'm right here. 1, 2, 3, 4 ways out of 36 possibilities total, or 1/9 is the probability of rolling 5. What's the probability of rolling a sum that exceeds or is greater than 12? Well, when I look over here, the two biggest numbers on each die is a 6. So the largest thing I can roll is a 12. What's the probability of rolling a number bigger than 12? 0. Can't happen. The largest number that can be rolled is a 12. Okay, what's the probability of rolling 2 even numbers? Well, let's just count those up out of my chart. Nothing in this first column counts in here, 2 even numbers, because one of them is always a 1. In the second column, no, I have a 2, 2, a 2, 4, and a 2, 6. Those are 2 even numbers. Okay, nothing in this column will be both even because one's always a 3. But over here, I've got a 4, 2, a 4, 4, and a 4, 6. Nothing here because one of them's a 5. But here's my 6, 2, 6, 4, and 6, 6. So if I count up the number of ways that my rolls can consist of 2 even numbers, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the probability of getting 2 even numbers is 9 out of a total of 36 possible outcomes, or 1 out of 4. Okay, what happened? I lost my page. Here we go. All right. Okay, what about this? This says this table shows the distribution by age and gender in millions of the 29.3 million Americans who live alone. Use the data in the table to solve the following problems. All right, so let's see what we have. Here's the row for males. Here's the row for females. Here's the column for age group 15 to 24, 25 to 34, etc., etc. Here's a total going across this way and a total down here. So find the probability expressed as a decimal rounded to the nearest hundredth that a randomly selected American living alone is male. So I've got to go up here, and here's my row of males, right? I go all the way down to the total, because it doesn't say a male that's, 15 to 24. It just says I want to find the probability that the person is male. So there's 12.5 million males out of a total of 29.3 million. Remember, we don't mix fractions and decimals, so I'm just going to plug that in my calculator as 12.5 divided by 29.3 to get 0.42666211 ... but it tells me to round to the nearest hundredth, so I'm going to round to the nearest hundredth, right, to get that probability is approximately 0.43, or about 43% of Americans that live alone are males. What about this? What's the probability that the American living alone is in the 25 to 34 age range? Well, here's my 25 to 34 age range. Okay, so here's the total of people 25 to 34 that live alone, and that's all it's asking about. So 3.8 out of the total 29.3 million. Plug that in the calculator. To get 0.1296692, but we're going to round to the nearest hundredth. So that's about 0.13, or 13%. Okay, what's the probability that you are, or that the randomly selected American is a woman age 15 to 24? All right, well, here's my 15 to 24, and here are the females that are age 15 to 24. Instead of just plain age 15 to 24, I need the women that are age 15 to 24. So 0.8 million out of 29.3 million total. Plug it in the calculator and we get 0.0273. I'm going to round to the nearest hundredth again, simply because that's what the instructions asked me to do. 0.03. Okay, think about this. Does the following statement make sense? Assuming the next U.S. president will be a Democrat or a Republican, the probability of a Republican president is 0.5. Does that make sense? No. Okay, remember, to determine these probabilities, they are based on equally likely outcomes. It is not equally likely that a Democrat or Republican will be chosen. There's a lot of other factors to consider from one election to the next. So it's not like a random drawing of a Democrat and a Republican. So no, that does not make sense. Remember that the outcomes have to be equally likely no matter what other factors are happening. Okay, that should cover us for the beginning fundamentals of probability, and we're going to continue to look at these probabilities in the next couple of sections. So let me know if you have any problems that we need to go over.